Welcome back to statistics. Here's two problems, one of which you've seen before and another of which is new. So the first problem is a SAT preparation company. They have a course for preparing people to take the SAT, let's say the math portion of the SAT, and they'd like to see whether their course works. And so they take a random sample of clients, they give them their course, and then they give them the SAT. And what they would do is then check to see if their sample data gives them evidence to believe that the course actually improves SAT math scores on average, right? The average nationally is around 500, so they'd be looking to see whether their sample data gave them reason to believe that their course improves the SAT scores on the math portion to some level above 500. The second kind of problem involves, let's say, a superintendent of some large school district, and maybe there's two different high schools in his district, and the superintendent is interested in whether the performance of students at these two different schools on the math portion of the SAT is the same or different on average. That's a different kind of problem. The first problem, the SAT prep course problem, involves trying to see whether the mean is the same or different than some fixed number, right? Like 500. Whereas in the second problem, you have a different situation. You're trying to see whether the means at these two different schools are the same or different from each other. There's no, definite number you're comparing them against. You just want to see whether the means at school number one are different than the mean at school number two. This kind of problem is called a two sample problem because it involves comparing means from two different groups. And so we do that by using sample data from those two different groups. It's these two sample problems that we want to talk about today. We're going to see, both in the case of confidence intervals and of significance tests, that there's a lot of commonalities between two sample problems and the single sample or one sample problems that we've been doing up to now. But there are some differences, and those differences come into play mostly in the details of the computations you do in building a confidence interval or in carrying out a significance test. So let's see what the changes are. Comparing two means. So as usual, I want to start with an example. This will be different than the SAT math example, but you'll see the commonalities, I think. Suppose the CEO of a national marketing firm wants to determine the difference in mean wasted time during an 8-hour workday for employees of her company at two different locations. Each person in a random sample of 10 employees from location 1 is asked about daily wasted time, and a sample of 12 employees from location 2 are asked the same question. Participants were guaranteed anonymity in order to obtain truthful responses, and that makes sense. There would be a response bias if a person had to admit, without the cloak of anonymity, how much time they were wasting. And there you see the data in those tables. The first line contains the self-reported time wasted in an 8-hour day from the 10 employees at location 1, and you have the same data for the 12 employees at location 2 there. And so the question we want to ask is, does the data give us statistically significant evidence for a difference between the true mean time wasted at work at the different locations? So again, we're not comparing the mean wasted times to some definite number like 2 hours or 120 minutes, but we're asking a different question. Do the folks at one of these locations waste time more or less, or maybe the same, as the folks at the other location on average? So it is a question about means here. And I have a box plot, side by side box plots of our data here. The box plot on the left is from location 1, the box plot on the right is from location 2. And you see pretty starkly that there is a difference between the distributions of the data in the two locations. The time wasted at location 1 has a lot more variation to it than the time wasted at location 2. And just looking at the data, it looks like there might be some differences between the means as well, right? Because it looks like, at least if you look at the medians, the median at location 1 is 118. The median at location 2 is 110.5. So there's a difference between the medians, and there's probably a difference between the means too, but that's not as stark, right? A difference of 8 or so minutes between the medians when the data itself is on the order of 110 or 120 minutes may not be that big of a difference. And so this actually points out an important point. When you're comparing distributions, you don't want to just reduce everything down to a question of the means or the medians. Those are measures of center, and of course they're valuable. We'll actually be focusing on them in this talk. But distributions can be quite different and yet have the same or nearly the same centers, right? And actually we're seeing an example of that right here. So again, the question we want to ask is about the means. Is there evidence from this sample data that the true mean time spent wasted during an 8-hour day is different between these two locations? Our analysis will focus on some summary statistics of the data, and you see those statistics here in this table. Basically, we're going to need the sample sizes from each location, the sample means from each location, and the sample standard deviations from each location. So looking at those summary statistics here, you see with respect to the means, something similar to what we saw with the box plots. That is, there is a somewhat of a difference between the means, but not a lot. A mean of 117.1 minutes for location 1, a mean of 113.9 minutes for location 2. So it looks like a difference there of about 3.2 minutes in the average times in the samples, right? Of course, we're interested in the larger question. Does this difference in the sample means give us good or statistically significant evidence for a difference in the actual population means? If we look at the populations of all employees at location 1 and all employees at location 2, would we see a difference in those population means? So in doing this kind of inference, there's really two approaches we could take, and those are the same as we've seen in one sample problems. We could look at the problem of estimating the difference between the true population means. The estimation problem is solved by a confidence interval. So we'll be looking at two sample confidence intervals in this talk. You could also test beliefs. You could test the hypothesis, the null hypothesis, that the two means are equal versus an alternative that says that there's some kind of inequality between the two means. And that would be a significance test for two means. So let's first look at the confidence interval problem of estimating the difference between the two means. What we're trying to estimate here is the difference between the population means, mu1, the average time at location 1, minus mu2, the average time at location 2. And our point estimate for that is just the corresponding difference between the sampling means, right? That makes total sense because the sample mean for location 1 is our best information about the population mean, mu1, and similarly, our sample mean from location 2 is our best estimate for the population mean at location 2. Just as before, this point estimate, x1 bar minus x2 bar, is an unbiased estimator of the difference between the population means. That is, the average value of the difference of sample means is equal to the difference between the population means. In other words, if you could look at the sampling distribution of x1 bar minus x2 bar, look at how that varies across all samples of 10 employees from location 1 and 12 employees from location 2, the mean of that histogram or dot plot, the balance point, would be the true difference in population means. So our point estimate is an unbiased estimator of the parameter we're trying to estimate, and that is the same as it was for a one sample problem. We also have information about the standard deviation of our point estimate. That's given by this formula here. The standard deviation of x1 bar minus x2 bar is the square root of sigma 1 squared divided by n1. Sigma 1 is the standard deviation in the first group. N1 is the sample size in the first group. Plus sigma 2 squared over n2, and then take the square root of all of that. The sigmas, however, are generally unknown in a two sample problem, and we've actually seen that that's also the case in a one sample problem. So we're not going to be able to compute exactly the standard deviation of our point estimate. But what we will be able to do is approximate it by using the sample standard deviations as estimates for the individual sigmas, sigma 1 and sigma 2. That results in the standard error of our point estimate. And so our standard error is just our estimate for the standard deviation of our point estimate. And the estimate is based on the sample standard deviations, which of course we can always know since we have sample data. We will use the standard error in place of the standard deviation whenever those population standard deviations, sigma 1 and sigma 2, are unknown. So we know the center of the sampling distribution, we know the standard deviation, or at least we can estimate it using the standard error. So what about the shape of the sampling distribution? Well, here the story again is fairly similar to what we saw in one sample problems. That is, the sampling distribution of our point estimate is going to have a normal distribution. This will be exactly true if the population distribution in both groups are normal themselves. And this again parallels what we saw in one sample problems. But even if those population distributions aren't normal, if the sample sizes are reasonably large, and by that I mean the sum of the sample sizes in both groups is at least 30, then except for all the most extreme cases, except for cases of extreme skewness or strong outliers, the sampling distribution of our point estimate will be very close to a normal distribution. And even if there is strong skewness, just jacking up the sample size a little bit more, if the total sum of the samples in both groups is at least 40, then you can rest pretty well assured that the sampling distribution of x1 bar minus x2 bar is going to be very close to normal. So let's see how some of these ideas play out for our data. I've got the summary statistics here in the table in front of us just so we can keep those in view, and we can compute the standard error of x1 bar minus x2 bar, and you see that computation here. It turns out to be 8.6391. So that would say that the difference between our sample means, right, that 117.1 minus the 113.9 and a little bit of change, that's about 3.2. That difference varies from sample to sample with a standard deviation that we estimate to be 8.6391. So in other words, our observed difference of 3.2, we wouldn't be surprised if that in another sample turned out to be one standard deviation more, right? Like 3.2 plus 8.6, something like, 11 or 12, something like that. We wouldn't be surprised if another sample gave us a difference between sample means that was one standard deviation less than our 3.2, something like, -5 or -6. That gives us an idea, this standard error gives us an idea of how much our difference in sample means varies as you go from sample to sample. And so that number here is about 8.6 minutes. So how are we going to use that? Well, because the population standard deviations are unknown, we're going to be using the t-distributions to do our calculations. And the t-distributions have, of course, the concept of the degrees of freedom that are appropriate. And here in a two-sample problem, there's a genuine complication, right? Because in a one-sample problem, the degrees of freedom for estimating a mean were always n minus 1, where n is the sample size. But in a two-sample problem, you've got two independent samples. We've got 10 measurements from location 1, 12 from location 2. Is the right degrees of freedom 10 minus 1 or 9? Or is it 12 minus 1 or 11? Or maybe it's our total sample size, right? 22 minus 1 or 21. Well, it turns out the answer is really none of the above. The degrees of freedom in a two-sample problem for a t-distribution are actually kind of complicated. You see the formula here. V1 is actually the sample variance from group 1, and V2 here, S2 squared over N2, is the sample variance from group 2. And the degrees of freedom is that rather complicated formula involving V1 and V2. If you actually plug and chug with our data, you find that the degrees of freedom for the t-distribution for our problem is 13.4417. The issue here is that not only is that formula complicated, but it's an approximation itself. That is, the actual sampling distribution that we're going to need for our test statistics and critical values and so on is not even a t-distribution. It's an even more esoteric distribution that's studied in more advanced courses. And so even using that formula, which is complicated enough already, is an approximation in itself. Now, it's a very good approximation. And when you do these problems using software, typically they're going to use that formula right there. But for our calculations and for purposes of kind of getting familiar with the concepts, we're going to use a much simpler approximation. It's called the conservative estimate for the degrees of freedom. And what it involves is simply taking the minimum of your two sample sizes and subtracting 1. And we'll use that for our degrees of freedom. That's called the conservative estimate for the degrees of freedom. And for our example, it works out, really simply, as it will for any example. We've got sample sizes of 10 and 12, so the minimum is 10. Take 1 away from that, and you've got 9. So the conservative estimate for the degrees of freedom is 9 for our problem. Why is it called the conservative estimate? Well, there's several aspects to the answer of that question. One is that this conservative estimate for the degrees of freedom, 9 in our case here, is always going to be less than the degrees of freedom that you would calculate from the formula. And that'll always be the case. So that's one aspect of the meaning of conservative here. Another aspect of it is that the p-values and the critical values and so on that arise from this conservative estimate are all going to be such that they give us kind of they err on the side of safety. So for instance, for p-values, right? You know that we reject the null hypothesis when the p-value is smaller than the alpha value. The p-values returned using the conservative estimate are going to be larger than p-values returned either using the software formula or even more sophisticated techniques. That means that it's going to be harder to reject the null hypothesis, right? Because the p-value would be larger than it normally would be with a more accurate approximation. So the p-value is conservative in the sense that it reduces the probability of falsely rejecting the null hypothesis. It reduces the probability of a type 1 error. Similarly, for a margin of error, the critical values and the margins of error that come from using this conservative estimate are going to be larger than what would be returned from the formula on the previous slide. And that means that the actual margin of error that you get when computing a 95% confidence interval, for instance, will actually give you more confidence. Your margin of error will actually be larger than what you need for 95% confidence. You'll get actually more like a 96 or a 97% confidence level when using the conservative estimate. So we're again erring on the side of safety. So we'll be using the conservative estimate for the degrees of freedom in all our work over this talk and the next several. Okay, so how would we put together a confidence interval? Well, here's where the story kind of reconverges with what we've already seen in one sample problems. In one sample problems, the margin of error was a critical value times a standard error. And the exact same thing is true here. The margin of error is going to be a critical value from a t-distribution, right, times that standard error that we discussed previously. What about the confidence interval itself? Well, remember, it's a confidence interval for mu1 minus mu2. So the confidence interval will be our point estimate, which is x1 bar minus x2 bar, plus or minus that margin of error. What about significance tests? Well, again, there's a convergence with what we already know in one sample problems. In a one sample problem, the test statistic for a test is essentially the z-score or the t-score, which is an estimate of the z-score, for your data, for the sample means. And similarly here, the test statistic in a two-sample problem is the t-score, which is an estimate for the z-score, of our point estimate. So it's the point estimate divided by its own standard error. And there you see the formula. And then the p-value for the test will be the area in the left, right, or both tails defined by the test statistic. And whether you have a left tail or a right tail or both tails depends on whether you have a left-tailed alternative, a right-tailed alternative, or a two-sided alternative. So all that is directly parallel with what we already know from one sample problems. Let's take a look at our example again. Again, we have the self-reported time spent wasted at work in an 8-hour day from both locations. Let's begin by finding a 95% confidence interval for the true difference, location 1 minus location 2, in mean wasted time per workday between the two locations. So let's just kind of walk through it. The data that we need is summarized in our table of sample sizes, sample means, and sample standard deviations. So the first thing we would do is pull out our point estimate for mu1 minus mu2. That is our difference between the sample means, x1 bar minus x2 bar, and that turns out to be 3.183. So on average, individuals in location 1 from our sample spent 3.183 more minutes, wasting time at work than did individuals in the sample from location 2. What about our standard error? Well, we've already done that computation. That's already our 8.6391 minutes. The degrees of freedom for the t-distribution, again, you take your minimum sample size between the two groups and then subtract 1, so that's going to be 9 in this example. Now we need our critical value for the margin of error. We have a 95% confidence level, so we need the middle 95% of the t-distribution with 9 degrees of freedom, again, using our conservative estimate of the degrees of freedom being 9. So we're just looking for the middle 95% of the t-distribution with 9 degrees of freedom. The upper bound for that you see in the picture is our t-star value, our critical value. That's 2.2622. We've got the critical value now. We also have the standard error. So the margin of error is just the product of those two. It's your critical value times your standard error. And that turns out to be 19.5434 minutes. So finally, our 95% confidence interval would be our point estimate of a difference of 3.183 plus or minus our margin of error of 19.5434. So that gives us a 95% confidence interval for the difference between means of negative 16.3604 up to 22.7170. So we're 95% confident that that true difference in population means is between our about negative 16.4 minutes up to about positive 22.7 minutes. Let's think about a significance test. Again, same situation. Does the data give statistically significant evidence for a difference between the true population mean time wasted at work in the different locations? Well, in a situation like this, our null hypothesis would be that there's no difference, right? That's typical for the null hypothesis. No difference, no change. And so we would write that as the null hypothesis that the difference between population means is equal to 0. The question we're asking is there evidence for a difference? We didn't really specify whether we thought one location was wasting more or less time. We just wonder if they're different. And so our alternative hypothesis will be two-sided. Is the difference between the two population means different than 0? So there are our hypotheses. And the 95% confidence interval actually casts light on this significance test just as it did before because it's two-sided, right? Our 95% confidence interval for the mean is from about negative 16.4 up to 22.7. What would we say about this? Well, the significance test is asking whether we can reject the null hypothesis that the difference in means is zero. Looking at our 95% confidence interval, we see that 0 is a totally plausible value for the difference between means, right? Because 0 is in that 95% confidence interval. So therefore, we can conclude that we would fail to reject the null hypothesis at the 5% significance level. That's because, again, the hypothesized value that the difference in means is 0 turns out to be totally plausible at the 95% confidence level, so we would fail to reject it at the 5% significance level. So this correspondence between confidence intervals and two-sided significance tests continues to hold in two sample problems. Why don't we change the question a little bit, though, so we can kind of see what happens in a one-sided significance test. Instead of asking do the means differ, why don't we ask whether the individuals in location 1 spend more time on average, goofing off, than do individuals at location 2. There, our null hypothesis would be the same, but now our alternative would be that the mean time spent at location 1 is greater than the mean time spent at location 2 goofing off, right? Or another way of saying that would be the difference, mu1 minus mu2, is bigger than 0. It's important to be able to look at sort of reason your way through that. Again, mu1 minus mu2 is greater than 0 in the alternative hypothesis because we're investigating the suspicion, the belief that the mean time at location 1 is greater than the mean time at location 2. If, on the other hand, you suspected that the mean time at location 2 was bigger than the mean time at location 1, right, then mu1 minus mu2 would be negative because you'd be taking mu1, a smaller value, and subtracting off a larger value, mu2. But here, the suspicion, again, is that mu1 is bigger than mu2, so if that's the case, mu1 minus mu2 would be bigger than 0. Let's carry out this test at a 10% significance level. So this would be a pretty weak significance level, right? We're not requiring a whole lot of evidence in order to reject the null hypothesis that the difference in means is 0. All we're going to be looking for is a p-value that would be less than 10%. Let's see what we get. We can't use a confidence interval approach here because the alternative is one-sided, but we can just go back to our data, compute a test statistic, and so on. So again, we've already seen this, but the point estimate is relevant here. That's the difference in sample means. We're going to need the standard error of our point estimate, so we've already computed that. Our test statistic is the best estimate we have for the z-score of the difference of those sample means. So it's the difference in the sample means divided by the standard error of that difference. And that turns out to be 0.3684. So the interpretation here is that we estimate that our sample data is about 0.37 standard deviations above where we would expect it to be if the null hypothesis were true, right? That's not a lot, right? That's less than half a standard deviation. In other words, our test statistic is saying it doesn't look like our sample data is inconsistent with the null hypothesis. It's only barely more than a third of a standard deviation above where we would expect it to be in the case of the null being true. So it doesn't look very extreme. Of course, the p-value quantifies just how extreme our data is, and so let's go ahead and calculate that. The p-value is the probability of all test statistics that are at least as strong as ours against the null hypothesis and in favor of the alternative. The null hypothesis is again represented by the mean of our t-distribution with 9 degrees of freedom. That's 0 here. It's the middle of our graph. Test statistics that are against the null hypothesis, that argue against the null and in favor of the alternative, are test statistics that are bigger than 0, right? Because our alternative is that the difference in the means is bigger than 0. Test statistics at least as strong as ours against the null hypothesis and in favor of the alternative would therefore be any test statistic that's bigger than our test statistic. So we would look at the probability of all t-scores that are at least 0.3684 or bigger. And you see that area shaded in our graph. It's the area to the right of our test statistic. And that area turns out to be 0.3606. So our p-value for the test is 0.3606. And so since that p-value is bigger than our significance level alpha of 10%, we fail to reject the null hypothesis at the significance level alpha equal 10%. And our conclusion would be that the data do not provide statistically significant evidence at the 10% significance level that the true mean time spent goofing off in location 1 is greater than the true mean time spent goofing off in location 2. So we have no good evidence that the mean time is either different or greater than between the two locations. So I hope you see that there's a lot of commonality between doing 2 sample problems and doing the 1 sample problems that we've been dealing with up to now. The differences mainly lie in the details of the standard error and the degrees of freedom that we have for our t-distribution. So let me know if you have questions. In the meantime, stay safe, and we'll talk again with you real soon. Y'all take care.